Alright, let's dive into the world of heap data structures. Think of a heap as a special type of binary tree that follows some interesting rules. Imagine you have a bunch of numbers and you want to arrange them in a certain way. Well, a heap is like a tree that helps you to just do that. But it's not just any tree, it's a complete binary tree. That means every level of the tree is filled up, except maybe the last level, and if there are any gaps, they are to the left. Now, here is the cool part. In a heap, each node has some special qualities. If you are dealing with a max heap, every parent node is always bigger than its child nodes. And guess what? The biggest number is right at the top, the root node. On the other hand, if you are talking about a min heap, it's the opposite. Every parent node is smaller than its children, and the smallest number is right up there at the root. And guess what? We call this whole heap thing when we are being a bit more specific. A binary heap. It's like a magical tree that helps us keep track of data in a way that's super efficient. So, whether you are aiming to have the biggest number on the top or the smallest, a heap is your go-to structure to make things organized and quick to access. Let's explore the important things we can do with a heap. Think of these as the cool tricks that can heap perform. I'll explain each of them to you. Alright, let's dive into a concept called heapify. It's like giving our binary tree a special structure so that it follows the heap property. Remember, a heap can be a min heap or a max heap. Here is how we can do it. Imagine we have an array of numbers. They are 3, 9, 2, 1, 4, and last we have 5. So at first, we create a complete binary tree using this array. And now, we start from the first non-leaf node in the array. Its index is given by n divided by 2 minus 1. We will call this current element the largest. The index of its left child is given by 2 times I plus 1. And the right child's index is 2 times I plus 2. If the left child is larger than the current element, we set its index as the largest. Similarly, if the right child is larger than the current element, we update the largest index. If the largest index is not the same as the current index, we swap the elements at these indices. We repeat these steps for each non-leaf node in a bottom-up manner. So this process is called heapify. So let's discuss the algorithm behind this. First, we start at a given index named I. Compare the elements at index I with its left and right child elements. If the left child is greater, set its the largest index. If the right child is greater than the current largest, update the largest index. If the largest index is not I, swap the elements at I and largest indexes. Repeat this process for each non-leaf node. To create a max heap, we loop from the first non-leaf node index down to 0. For each index, we call the heapify function to ensure that the subtree rooted at the index follows the max heap property. For a min heap, the comparison is reversed. Both left and right children must be smaller than their parent. This way, we can reorganize our data in a way that it's efficient for various applications. Alright, let's learn how to insert an element into a heap, like adding a new student to a seating arrangement. So we will focus on a max heap for now. So here is how we can do it. First, check if there's no node in the heap. So if it is empty, just create a new node with your data. But if there are already some students, which means nodes in the heap, put the new student at the end, on the last row from left to right. After adding the student, we need to make sure the arrangement follows the rules. So this is where heapify comes into play. It's like adjusting the seating arrangement to maintaining the order. If there are no nodes, create a new node with your data. If there are already nodes, put the new students at the end of the arrangement. This is kind of like adding a new leaf node at the end of the tree. So after doing inserting, we do heapify. This means we adjust the arrangement so that the larger students are on top following the max heap rules. For min heap, the process is similar, but this time we make sure that the parent node is smaller than the new node. So in this way, the smaller students are at the top. In simple terms, imagine you are adding a new member to a club photo. You put them at the end of the row and then you adjust the height of everyone's so that the tallest people are in the back for a max height or the shortest are in the front for a min heap. This helps in keeping things organized and efficient when working with data. Alright, let's dive into how we can remove an element from a heap, like taking a student out of a seating arrangement. We will focus on max heap for now. So here is the process broken down. First, you choose the student you want to remove. This is like picking the person you want to take out of the arrangement. Then you swap the students with the very last student in the arrangement. Think of it as if you are swapping the student you want to remove with the last person in the row. Once the swap is done, you can take out the student you want to remove. It's like removing the student from the group photo. But wait, we need to make sure the remaining students still follow the rules. This is where heapify comes into the picture again. We adjust the arrangement again to maintain the order of the tree. So these are the steps of the algorithm. Choose the student you want to remove. Swap that student with the last student in the row. Remove the student from the end, which is the last node. Heapify the arrangement to make sure the tallest students are still at the top for max heap. For min heap, the process is similar, but this time we make sure both child nodes are greater than the parents, so the smaller students are still on top. To put it in real world terms, think of it like removing a friend from a group picture. You swap them with someone at the end of the line. Then you remove them from the picture. And of course, you adjust everyone's height so that the tallest ones are still in the back for a max heap, or the shortest are in the front for a min heap. This helps to keep your data organized and efficient. Alright, let's talk about the peak operation in heaps. Imagine you have a line of students and you want to find out who's the tallest for max heap or the shortest for min heap without actually removing anyone from that line. Here is how it works. When you do the peak operation, you are simply looking at the very first student in the line. This student is like the root node of the heap. For a max heap, that student will be the tallest among all, and for a min heap, they will be the shortest. Now, here is the nitty-gritty in simple terms. You do the peak operation. Then you see the student at the very front of the line, which is the root node. Then that student will be the tallest for max heap or the shortest for min heap. Think of it like checking who's leading a parade. The student at the front is the leader, either the tallest or the shortest, depending on whatever it is, max heap or a min heap. And you are just checking it without making any changes to the arrangement. Now, let's dive into the extract max and extract min operations in heaps. Imagine you have a collection of items like a bunch of toys and you want to take out the most valuable one for max heap or the least valuable one for min heap. Here is how these operations work. Extract min operation. First, you look at the heap. You pick the item with the highest value from the collection. You remove that item from the heap, and then now the heap rearranges itself so that the next highest item takes the place for the one you removed. Next we have extract min operation. First you look at the heap. Then you pick the item with the lowest value from the collection. Then you remove that item from the heap and the heap adjusts itself, making sure that the next lowest item is now at the front. So, if you have a heap of toys, for instance, and you do an extract max, you are getting the most valuable toy. But if you do an extract min, you are getting the least valuable one. Think of it like picking the best or the least preferred item from a collection and then letting the collection reorganize itself. It's like taking out the shiniest gem from a treasure chest and letting other gems shuffle into a place.